All right, howdy everybody. Welcome back to Professor Carbon. And so it's been a real treat to provide these videos and upload them. And so what I'd like to do first off is thank those of you that have already subscribed to our YouTube channel. If you have not already done so, please click the little subscribe button. That really helps provide encouragement to continue uploading these videos. In this particular video, what we're going to do is go over this slightly more complex reaction sequence, which is outlined here. And what I would tell you is this is really probably for the students that are at the edge of Organic 2, maybe even transitioning into an upper level organic class or graduate school. And some of these reactions might be new, as are some of the reagents to many of the viewers here. Okay, as always, what I would encourage you to do is to take some time and try to do this video before you listen to me talk through it. And if some of these reagents are new to you, or if some of the acronyms are new to you, what I would encourage you to do is just put into your Google search bar or Safari, the reagent, and then put organic chemistry or organic synthesis next to it, and you can probably get it to pop up relatively quickly with a decent description of what that reagent is or what it does, either on Wikipedia or from a chemical vendor or some other source like Organic Chemistry Portal. So please go ahead, pause the video, and try to work through this problem all on your own right now. Okay, welcome back. What I'm going to do is just talk this one through. And there's a lot of fun stuff in this particular one. And so let's just go ahead and get started. The first reagent here is going to be tosyl chloride with triethylamine and DMAP. And if you're new to DMAP, it is dimethylaminopyridine, which is this reagent shown here. It turns out to be a really good nucleophilic activator at the pyridine nitrogen, and is also a modestly strong base. And so this is going to be used as a catalyst to promote the formation of a tosylate. And that tosyl chloride, of course, converts an alcohol into a good leaving group in the form of its tosylate. Now, if you look, our molecule has not one, but two potential alcohols where this could react. And if we look carefully, we'll see that it specifies one equivalent. So what that means is one of these two alcohols should preferentially react with that reagent. And in this particular case, it's going to be this one because that one is going to be more sterically accessible. If we look at it, this alcohol is primary, but it's next door to this tetrasubstitute carbon or quaternary carbon. And so we call that alcohol neopentyl. Coming from neopentane, which is kind of the 5-carbon plus sign molecule, if you will. All right, so let's just go ahead and sketch out what that product would be then. We're gonna have a double bond there, and then this will now be OTS. We'll still have those pieces like so. All right, now the next step here, step 2 is gonna be sodium cyanide. And this sodium bicarbonate is really going to be mostly a safety precaution. So sodium cyanide, of course, is quite toxic, being that it's cyanide. But what is even more toxic than sodium cyanide is hydrogen cyanide, HCN. And that's because HCN is a gas, whereas sodium cyanide is a salt. And so there's an increased risk that you might inhale it or smell it if it went up into the air. So by keeping it basic, we'll prevent HCN from forming. And so that is a key consideration here. And cyanide, of course, is going to be a fantastic nucleophile. And we're going to take advantage of having made that other alcohol into a good leaving group before. So we're just going to do an SN2 reaction there. Like so. Okay, now this next step is one that might be new to you all, or at least some of you, SO3 pyridine with triethylamine and DMSO. It's actually going to be the Pyrrhic Doring oxidation. And these reagent combinations are actually going to convert alcohols into aldehydes. And so some of you might be more familiar with reagents like PCC or chromium or chromate, so H2CrO4, a so-called Jones oxidation. These involve that chromium metal, and of course that's a heavy metal which is environmentally toxic. And so one advantage of using SO3 pyridine and triethylamine is these are not heavy metals. And so because of that, it's a slightly more environmentally friendly and perhaps less toxic approach than using the traditional chromium reagents. But thankfully, we do have a primary alcohol to oxidize up, so that'll get us to the aldehyde. And if you search those reagents, you should be able to come up with that named reaction. The next step here is going to be a fun one. So LHMDS is going to be lithium hexamethyl diacylamide. And it's going to be a bulky non-nucleophilic base with a relatively high pKa. And so some of you may think about it being akin or equivalent to lithium diisopropylamide or LDA. And so that's usually a base that's introduced later on in the chapter for a lot of enolate chemistry. And in this case, LHMDS is just a kind of a nice equivalent of that. That's sometimes better, sometimes not as great. And in this case, it's the one that the authors of this work chose. So speaking of aldol-like chemistry, it's going to end up deprotonating this H because that nitrile is a pretty good electron withdrawing group, and there are no hydrogens that can be deprotonated next to the aldehyde. We definitely do not want to deprotonate there. Don't deprotonate the aldehyde. But this H here is going to be a good one. And so then eventually that position will attack the alcohol there. And if we count, that should be a, just switch colors here. So 1, 2, 3, 4, 5, 6-membered ring. So we're going to end up making a new ring. Look at that. All right, and now we're also going to make a new stereocenter right here. And so that'll be something that we have to consider. And we're going to have a new stereocenter right there. So we have 2 different new stereocenters that could form. And so potentially that could cause quite a big problem. But for reasons we'll see in a little bit, it's actually not going to matter so much, which is kind of a nice trick that these authors used. So the last step then is going to be to convert this to an acetate using acetic anhydride. And usually when we convert an alcohol to the acetate, we use a base called pyridine. Sometimes if we really want to try to push it, we might use a base as strong as triethylamine, the structure I can draw here. But DBU is a much stronger base than we would often use for this reaction. And so that's a clue something else might be going on. And so I'm gonna and so the acetate will get us to here, but with DBU, we're actually going to be able to deprotonate the second hydrogen that was all the way over on this side, and we're actually going to kick off that acetate. So by going from the OH to the OAC, we've made it a better leaving group, and then we can use a base like DBU to actually promote its elimination. And this question now asks, does this stereochemistry that we were looking at or thinking about up here matter? And the answer to that, you should think about while I draw. So this will ultimately be the final product of the sequence shown here. But we might want to, just think about what is the arrangement or mechanism by which that acetate leaves. Certainly if it's an E2 reaction, we would require an anti-periplanar relationship. I don't think it's really set up very well for an E1 reaction, but there is what is sometimes termed an E1CB reaction, which I think this would fit into. And so it doesn't really matter. Squiggle here means that it could be both wedge or dash, and we don't know, and there's probably a mixture. But if we think about having a negative charge here with that cyanide, or nitrile, excuse me, we then could imagine a resonance structure where we delocalize that negative charge into the nitrile and put it on the nitrogen. And this resonance structure, of course, really helps us explain why nitrogen, or why these CN groups are powerful electron withdrawing groups. But what's probably more important about it now is this carbon in this resonance structure is flat. And it's, has that p orbital sticking up above and below the ring system. And what's significant about that then is it won't matter if that OAC is up or down. The p orbital from that carbon is going to be aligned with the antibonding orbital in both arrangements. And so we can draw then a nice elimination reaction like so that ultimately kicks off acetate anion, and should occur regardless of the stereochemistry. So to put it differently, the stereochemistry on this first center here that I'm circling in blue won't matter, because ultimately we're going to make this anion that no longer has that stereochemical information. And then the stereochemistry of the OH containing carbon that I'm circling here ultimately won't matter, because it's going to be lost through an E1CB mechanism that is insensitive to that stereochemistry. And so that's awfully cool. All right, so that summarizes this nice reaction sequence. What's fun about it is it's, a lot of steps, of course, so 5 is a good number, but it does show some really nice functional grouping and conversions, some of which are very classic from first semester organic, converting alcohols to tosylates using cyanide and SN2 reaction. It also introduced us to some new reagents like the Pyrrhic Doring oxidation, as well as the use of lithium hexamethyl diacylamide. And we had some fun with stereochemistry at the very end, where ultimately for this particular reaction, the stereochemistry was not super important. So with that, hopefully you've enjoyed this video. Please stay tuned for our other ones, and I'm looking forward to any comments you might leave.